All right, I'm having some technical difficulties with Zoom today. Can you guys hear me?
Yeah.
Okay. All right. Thank you. All right. And admit some of you. Okay. All right, so people are filing in. It's a little slow today. How's everybody doing with getting all the assignments done? All right, well, listen, so we have a few things going on right now. You have a homework that's due tonight, and you may have questions on the homework that I would be happy to help you with. The material that's on the homework that has to do with line integrals, I would like to discuss that in more detail today. But if you have questions on the path integrals and the surface integrals, we can discuss that before we get rolling. Just one thing I will say to preface all of that, at this point you guys have seen a lot of different types of integrals, and one of the tasks that seems to be tripping a lot of you up is just deciding which kind of integral it is. So let me say that the path integrals and the surface integrals are the ones we've been spending the last few days on, and you will recognize those as distinguished from any others because those have always a real valued function in them. And by that I mean it's a function that takes points, x, y, z, say, and from those coordinates it just computes a single number. If you have just such a function written out, usually the book's notation, the Quest notation, it's always with no boldface. Everything is just in ordinary font. And the meaning in both of those cases then is you're just taking that function and you're evaluating it at different points on your set. Obviously, as always, we're multiplying the values of the function times the sizes of the pieces around it. At that point, the only thing you need to do is to distinguish the path integrals from the surface integrals. And obviously, the difference there is you have to decide, are you being asked to integrate over a one-dimensional set, that means a curve, or are you being asked to integrate over a two-dimensional set, which is a surface? So that's the first step, is just to recognize, do you have a path integral or a surface integral? Or the other thing that you see already in the homework, and you'll see it on the test too, I guess, will be these things called line integrals, and they're distinguished by a few things. One of them that distinguishes them is, well, there's boldface written down, and when you see the boldface in that notation, that's always a clue that somebody's talking about vectors. More precisely, a vector field has to be part of the set of ingredients to these integrals somehow. So they would have to somehow be specifying a vector field for you. And the notation will probably also involve a big bold dot because there's a dot product involved. They might use little arrows over the symbols just to reinforce the fact that these are all vectors. So that's the stuff that's newest. We only started talking about that last time. I have more to say about it today to make you feel comfortable. There's slightly different types of integrals, or more precisely, they're going to turn into the same path integrals that we've already been working on, but there's like a preparatory step to get a path integral. We're going to have to take that vector field and somehow mush it with some other components, and then that'll give us the function to integrate. So when you're looking at the homework, are there any questions that you have, anything that you're uncertain about that's just about the path integrals or the surface integrals, not the line integrals? Any of those that you need to ask me about?
I'm having trouble on problem 6 and 7.
All right, let me pull that up. I think I have that. Oops, maybe I closed that tab. I'm a very bad computer user. I have way too many tabs open at once. So let me log into Quest. Nathan, why don't you tell me what the question was? I can start writing it out.
Okay, one moment, please.
Let's see if I can pull it up faster than you. So this is homework 10, obviously. And it's not loading. Oh, here we go. Okay, problem 6 and 7 from the current homework. So my version says, for problem 6, it says, well, see, this is a vector, a line integral. It says, use the fact that blah, blah, blah is a gradient vector field to evaluate this line integral. That's problem 6 in my listing. But if that's the one you're asking about, I want you to not ask that right now, because that's, you know that it's a line integral for several reasons. 1, it says line integral. 2, you see boldface. And 3, you see a dot in the middle, which indicates a dot product. And while I'm at it, 4 is that you also see a clear vector field shown. So that's an example of a line integral, and we talked about them on Monday, but I know you guys are a little bit at loose ends on that one because we haven't discussed the line integrals yet. And problem 7, is that the other one you asked about? That's a line integral as well. So let me not answer those. Question 5 is a line integral. Question 4 is not a line integral, it's a path integral. And the difference there is that there's no boldface, there's no dot in the middle, there's no little arrows, there's no mention of a vector field. So that's problem 4 would be one of the ones that we've been working on for the last few days.
So I'm having a problem with 2.
Number 2, let's see that one. Find the mass of the wire formed by the intersection of this sphere, the given equation, and the plane in the given equation. So before you do anything else, tell me this, what do you get when you intersect a sphere and a plane? What kind of set do you get?
Circle.
You get a circle, right? I mean, for starters, here, let me share my screen because you guys don't want to look at me. So there, you should see my version of the problem in front of you. I've actually got the answer key, so you can start cheating. But they phrase the question in words, which is great. So you know that you've got a sphere and a plane, and you know that the sphere and the plane intersect in a circle. You also could just stare at the equations. Between the two of them, these are 2 equations in 3 variables. 3 minus 2 is 1. So you know that this is a one-dimensional set. This is a curve. And they've given you a curve, and they want you to integrate a function. Here's a function of x, y, and z. Okay, it's just x. But it's a function of the 3 variables, a scalar valued function of the 3 variables. And they do actually want you to integrate that function over this set. How do I know? Well, it's because that's how you would find a mass. You find the mass of an object by multiplying its density times its size. And the density is given in grams per centimeter. So we would need to know the size in centimeters. Unfortunately, the density is varying as you move along the curve. So you have to break the curve into little bits on which the density stays more or less constant. Okay, so that's obviously a perfect setup for an integration problem. So now let me take the screen back and turn the camera on. Show you what they're asking me to do. So apparently you guys are telling me that it's easier to see with my light turned off. All right, so the problem as I read it is you've been asked to integrate this density function, and it was 2x squared if I remember correctly. Integrate that with respect to length over this circle. I'll just draw a circle for you. And you've got a set, and you've got a function defined on the set, and you know how you're going to be measuring sizes of the pieces. So that's an integral. And since this is a curve, this is a path integral, which means that we should be able to evaluate this thing by beginning by parameterizing the curve. And as soon as I get a parameterization, so this will go from some interval of real numbers into 3-dimensional space. I will use the formulas, the three components of this function phi. It's got three components. I'll turn this into a function of t. I'll figure out what range of t's that I need to describe the whole circle, and I'll have to multiply by the fudge factor that we always get, the magnitude of the phi prime, the velocity vector. So how are we going to parameterize that circle? Well, it's a little tricky. You might think, oh, circles, that's a sine and cosine thing. But you know, you have to choose, you have to write all of your x and y and z coordinates as being functions of time. Those will be the three components of this function phi. But you have to choose those functions of time in such a way that at all times t, you don't leave the sphere. You always have to have x squared plus y squared plus z squared equal to 1. And at the same time, you have to not leave that plane. So you need, what was it? X plus z equals, I don't remember what the equation was actually. X plus z equals 0. So I have to choose functions of t that satisfy both of these equations at once. If you just take x to be cosine of t and y to be sine of t, then x squared plus y squared is already equal to 1, so you have to have z equals 0, and that's not going to work here. In fact, what you could say is, oh, look, my x and z coordinates have to be negatives of each other. So whatever I use for my x component, I'll write down the negative of that for my z component. And then I'll only have to pay attention to the x and y components. I will have got this part matched automatically, and all I will need now is I will need to have x squared plus y squared plus negative x squared equal to 1. So really what I need out of these three functions is I need to have 2 x squareds plus y squared equal to 1. Now this actually parameterizes, this equation describes an ellipse in the xy plane. In fact, it's related to the circle that we're actually integrating over. That circle that we're integrating over, I'm not going to spend too much time trying to draw it in three-dimensional space, but it's a circle that lies as a part of the unit sphere, but it's also a part of this plane of points whose x and z coordinates add up to 0. So if in the xz plane, you find the line of points where z is equal to negative x, and then you stretch that in the direction of the y-axis. That's the plane of points where x plus z equals 0, and it meets the sphere in this circle. When I eliminated the z components using this formula to get this relationship just involving x's and y's, what I'm telling you would be what there is to know about the x and y coordinates by themselves when you take this circle and you project it to the xy plane. So part of this has to be, you have to get its shadow going down, and there's another part of it over here where you have to sort of pick it up to the xy plane. So don't rotate it, don't spin that circle in space. Instead, you shine a light and you look at the shadow of the circle on the plane. And if you have a tilted circle, look, here's a circle, but when I tilt it, you see that it starts to look more and more elliptical. That's the ellipse that I just found the equation for. Well, how do you parameterize this ellipse? I think we did parameterizations of ellipses earlier in the semester, and we discovered that you could basically use the cosine and sine functions, but to account for that 2 that's sticking out there on the left, you'd have to take x to be 1 over root 2 times the cosine, and then y could just be a sine itself. So this is what I would take for the first component of my parameterization. This would be the second component of my parameterization. And I already know the third component should just be the negative of the first. So I'll have z equal to the negative of 1 over root 2 times the cosine of t. There's my phi 3. And I invite you to check that if you take x squared plus y squared plus z squared, you will always get 1, so you will never leave the sphere. I invite you to check that the x component plus the z coordinate will always be 0, so you will never leave the plane. So you're always in the intersection of the sphere and this plane, which means that you're always on that circle. And in fact, if you simply take values of t that go from 0 to 2 pi, you will parameterize the whole ellipse down here. So wherever it is that you're moving on that slanted circle, your shadow will move all the way around this ellipse in the XY plane. So now you're ready to go. Go all the way back to the original problem and change the three components so that they refer to t's instead of everything else. The range of t's that you need is you need to take t going from 0 to 2 pi. The value of the function has now been written as 2 times 1 over square root of 2 times the cosine of t. That's what has to be squared. And then you know you need to multiply by that fudge factor. It's always going to be the magnitude of your velocity vector, phi prime of t, integrated with respect to t. So I have to come back to my parameterization and compute x prime, y prime, and z prime, and look at the magnitude of that vector. You will discover actually that, well, I'll do it. X prime will be minus 1 over root 2 times the sine of t. Y prime will be just cosine of t. And z prime will be the negative of the x prime. And when you take x squared plus z squared, that'll turn out to be exactly sine squared of t. When you add in the y prime squared, which will be a cosine squared of t, now you're up to exactly 1. So this little fudge factor in our case turns out to be exactly a 1. And so your whole integral will just turn out to be the integral from 0 to 2 pi of cosine squared of t dt. And I happen to know that that comes out to a pi. Does that answer your question? I sped up at the end because I know that you guys know how to integrate a function of one variable. The hard part for you is the transition between the line integral, excuse me, the path integral in the first place, how you transform that into a Calc 1 problem. And the transition always comes from finding this parameterization. This is the key. You got to parameterize in order to compute these integrals. And I wouldn't have spent the extra time on this one problem, except, you know, that's going to be a good little bit of preparation for the last topic on line integrals. We started the line integrals on Monday, but I want to spend more time on that today. So, does anybody have any final questions on this one, or can I turn now to the line integrals? All right, let me set these aside. I'm done with that. Where's my line integrals? Here. Look, I wrote out the slides in advance this time. I'm trying to get a little organized. You can't see this. All right, so what are line integrals? Well, these are going to be integration problems that arise in a natural way in like a physics type setting. And what we're going to do is, as we think about what it is we're trying to accomplish, we'll realize that they are the same as the path integrals that I just did, these kinds of things. But I want to see how we get there. So the setting for line integrals is you've always got a path, and then in addition you have not a scalar valued function like this density thing. That just gave me a number at each point. Instead, for whatever reason, you've got a vector field floating around, so that at each point x, y, z in space, you can calculate a vector with 3 components, and all these little arrows are flying around. You can think of this as being, for example, a force field. It's the wind or gravity or something, and that force is affecting you as you walk along the curve. So, so right away, this is an indication that line integrals are going to be a little bit different. They are like the problems 5 and 6, or 6 and 7. I forget which ones they were on the homework, because you see a vector field. That's just the big difference. But from a physics standpoint, often what you need to do is you need to wander around on this curve. You're going to break it up into a bunch of little parts. Sound familiar? And you're going to multiply the sizes of each one of those pieces times what? What do you do with a vector field? You could look at the magnitude of that vector field. But somehow, the fact that it's vectors all the time, vectors having directions, somehow that might be relevant to you in a physics setting. And specifically, you might need to be evaluating this function. Now, you guys who have gone through a physics course know how this kind of thing happens. You have a force which is pulling you in a certain direction, but you're constrained to move in a different direction. Like when you pull on a wagon as you walk, you're actually pulling upwards a little bit on the handle of the wagon, even though you're constrained to walking along the surface. Or the wind is pushing you in this kind of a problem. So how much work the wind is doing on you, that's the opposite of the work that you would have to do if you're fighting the wind. The work that the wind is doing on you would be, you need to know how strong the wind is, that's this factor, but it's not doing any work if it's blowing perpendicular to your direction of motion. It's not actually moving you if you are constrained for whatever reason to stay along this path. The amount of work that it's actually doing is found by multiplying the force of the wind, but that gets reduced by the cosine of the angle between the direction the vector field is pointing and the direction that you are going to be forced to move. So this is the kind of application that I set up for you on Monday as well. You get the amount of work that's done as you move across a little distance by multiplying the size of the force times the distance that you travel. Force times distance gives you work. You add up the amount of work that you do on every one of the little pieces, it gives you the total work that you've done. Of course, this is all just an approximation because the force might be varying continuously, and so you have to chop up the pieces finer and finer. You take some kind of a limit and see what you get. And then this will represent something it has an application from like a physics standpoint. Okay, there must have been something that you wanted to compute that involved that force field or a vector field in the first place. Now, as mathematicians then, the physicist or engineer comes to us with this kind of a problem, and we recognize that, oh, yeah, you had a vector field, but you know what? You're just evaluating some scalar valued function. This is now just a number at each point, and you'll be multiplying those numbers times the size of the piece and so on, and we as mathematicians say, well, that's just what we call a path integral. So the line integral is no different from the path integral. The only difference is how you get to a path integral in the first place. You're no longer just given a function that represents a density or whatever. Instead, you have to do some work to start with the vector field and mush it around with all of those angles to get the scalar that is to be integrated. So that's what I'm going to do with you. I'm going to show you the steps you would have to go through to actually get that function f, the function to be integrated. How do you get it from the vector field? So, well, this is the recipe. It says you wander to each point on the curve, each point x, y, z, and on each point on the curve, you're going to figure out what the current vector is right there. And now you have to multiply by the cosine of the angle between where the force is pointing and where you're going on the curve. Cosines are nasty, but we know one way that we can make them show up in a formula. This is exactly what you would get if I had asked you to compute a dot product of the vector field with a unit vector that's pointing in the direction that I showed. I say unit vector because in general, one of our formulas for computing dot products is you could multiply the magnitude of the first vector, which is shown here, times the magnitude of the second vector times the cosine of the angle between them. And there's no room in this previous line for the magnitude of u, so I want the magnitude of u to be 1. That's why I wrote unit vector in there. Of course, you don't really have to have a unit vector. If you took any other vector that points in the right direction, then f dotted with v would be, yeah, it's that thing times the cosine times the magnitude of v. And if you don't want the magnitude of v in there, you have to divide it off. Or equivalently, you take any tangent vector, and if you divide it by its length, you'll get a unit tangent vector. So when you are given this kind of physics setup and somebody asks you to compute this integral, as a mathematician, you can set up this function to be integrated by performing some kind of a function with dot products in it. And that, at least it doesn't appear to talk about trigonometry anymore. That's nice. So I'm actually going to do an example just with that setting. Here's a vector field in the plane. So at each point x comma y, this computes a vector for you. And I've computed a few of them at different points along this circle. I've evaluated what this vector field is, and so I've drawn these vectors. Some of them are shorter, some are longer, and obviously they all point in different directions. So you could imagine that somebody wants to wander along this curve, and they say, well, yes, that's the force that I'm going to fight, or the force that's pushing me. And so what I need to do is I need to keep multiplying the size of that force times the cosine of the angle in the middle, and so on. In other words, they want you to compute exactly the sort of thing that I discussed up here, which will be a path integral. But I want to get this to look simpler, and here's my way that I'm going to do it. I just need to find a vector that's tangent at each point, and I'll divide by its length to get the unit tangent. I'll take the dot product with capital F, and that'll get me the thing with the cosines. So it's all good. So where's that tangent vector going to come from? Here's what I know about circles. Circles are special. Circles are easy, because if you draw the vector that goes from the origin out to where you are, that vector is always perpendicular to the surface. That's always a 90-degree angle in there between the vector that got you to the point from the origin to where you are. These are the same vector twice. That vector is always perpendicular to the tangent of the circle. And the vector that takes you from the origin out to a point, x comma y, is the vector x comma y. The reason I'm talking about that is if I know that that's a vector that's perpendicular to the tangent, well, then the tangent will be something that's perpendicular to this. And I know an easy way to get a vector that's perpendicular to any other vector in the plane. You just switch the components and throw in a minus sign. See, when you compute the dot product, you'll get xy minus xy. That's 0. And if the dot product is 0, these two things are perpendicular. So if that's perpendicular to the tangent, well, then this must be a tangent vector. All right, I've got what I needed. I needed a vector that's tangent to the curve at each point. And so I'll just compute this dot product, and I'll divide it by the magnitude of the vector. So here I go. Here's the vector field. They showed it to me in the top line. There's my tangent vector. And I just said I'm going to divide by the magnitude of the tangent vector. And I'll leave it to you guys to compute the dot product. It's this times this, minus this times this, or plus this times that. So there it is. The magnitude, you know how to compute the magnitude of a vector. All of this simplifies a little bit. I multiplied out the top. Since I am staying on the circle of radius 2, all of those magnitudes are always a 2 in my case. So now I have computed exactly this thing that I said was going to be the same as the thing I was supposed to integrate. I've given you now a scalar valued function that I have to integrate over the upper semicircle. This is the way the problem was given to me, is the physicist said, I need you to integrate across this arc. I need you to integrate this thing that combines the force vector field with something that has to do with the directions. And then we have just gone through the steps of turning that into one of these path integral type things that we know how to compute. All right, you see a scalar valued function of x and y now. And so you compute this just the way I did here. I reminded you how we compute a path integral. You have to start with a parameterization. You get x and y as functions of t. You shove them in, blah, blah, blah. You know, the drill. So that's it. That's how a line integral comes into being. And then this is how you do all the computations. Now, I do have to give you a warning, which is that at some point in the computations, I said I needed to have a tangent vector to the curve. And I got that in this moment by saying, oh, look, that's something that's perpendicular to the curve. So if I just swap the coordinates and throw in a minus sign, I'll get something that's tangent. And that's all correct. But I could have put the minus sign on the other side. That would have been a different vector that's perpendicular to this one. And therefore, that would have been a different tangent vector. That would have been exactly the negative of the tangent vector that I already wrote down. So that's going to make a big difference. When you go through the steps that I did to evaluate this quantity, if you replace v by negative v, well, you won't change the vector field, you won't change the magnitude, but you will change the sign of v. You'll get exactly the negative of the dot product you had before. So choosing one tangent vector instead of the other one gives me exactly the negative of the different integral. So your question should be, how do I know which one I'm supposed to compute? And the answer is not really a math answer. It's the application that will tell you. You have to decide, going all the way back to the original question, just if I could blow up that part of the picture a little bit, when you're standing at a point on the curve and you feel the vector field is pointing you that way, but you know you have to travel along this curve, you tell me I'm supposed to multiply the magnitude of f by the cosine of the angle theta, but there's two choices for theta. Did you mean this one or did you mean that one? They're supplementary angles, they add up to 180 degrees, so their cosines will be negatives of each other. So you have to decide, did you want to be taking the dot product with this tangent vector or that tangent vector? And well, the math can't tell you. It's the application that'll tell you which of these two you should have started with. Okay? Now, if you get the wrong one, the worst price that you will pay is that you'll be off by a minus sign at the end. That comes out from the math. But you know, that could be a big, it could be a big difference to know that my bank account balance is going to go up by $1 million versus knowing that it's going to go down by $1 million. So, so you do have to look at the application. Are you trying to figure out the amount of work that the force is doing on you as you move that way? Or are you trying to talk about the amount of work that you have to do to fight the force because you're moving that way? It's going to make a difference that only the application will tell you. All right, so keep that in mind. In practice, we're going to have to put little arrows on our curves just to indicate which way we intended to go. These, the arrows are supposed to be indicating which choice of the vector field which choice of the tangent vector we want. You'll be able to see how it compares to the vector field in the first place. So that the notation will start to involve little arrows just to distinguish those two. All right, now, this computation that I did for you, I was able to find the tangent vector because I had some nice geometry. The geometry of a circle is very special. It enabled me to find those tangent vectors by looking first for the perpendiculars. Most curves, that's a lot harder. For most curves, it's kind of hard to describe a vector that's tangent to the curve at each point x comma y. I mean, well, there are things that you can do depending on how the curve is presented to you. But the easiest way to handle it is if the curve is presented to you parametrically. And that's where I'm going to go with this again. Now, see, once you get to the point of reducing things down to a path integral, you know how we're going to have to start doing these computations. We're going to have to begin by parameterizing the curve anyway. So, if you have to compute a line integral, let me encourage you to start with that parameterization. Figure out where you should be at all times t in space. Because if you know where you're supposed to be at each moment, then when you compute the derivative of your position, what you will get will be a velocity vector, and you know that the velocity vector always points along the curve. So that can be your tangent vector. Just use the velocity vector that goes with your particular parameterization. Of course, if your friend parameterizes the curve with a different parameterization, you guys will get different velocity vectors. But it won't affect the value of the integral, as you'll see in a few minutes. All right, so then what are you going to do? Yeah, make sure that your velocity vector is pointing in the direction that your application requires you to do. So now, how are you going to get the function you're supposed to integrate? How am I supposed to get my path integral? We know that you're supposed to be taking the vector field dotted with a unit vector or the tangent vector divided by its length. But now my formula for the tangent vector is I'm just going to use this derivative, phi prime of t, my velocity vector, and I'll be dividing that now by the speed. So this is the function that I'm supposed to integrate across the path. When somebody asks you to compute this, I've already shown you that it's supposed to be the integral of this function little f evaluated on the path. And as you start computing this path integral, you need a parameterization. And we use exactly the parameterization we're already using. So then you know you change the three parts. You change your region of integration to be the range of t's that you need. You do have to rewrite your integrand, and this looks horrible, but it's exactly the same integrand as I had over there. It's the value of the vector field dotted with this unit vector. Now, the unit vector is already written out with t's in it. The vector field was given to me, if you think about the last example, it was given in terms of x's and y's and z's, but I know what my x, y, and z coordinates are supposed to be at each moment in time, so this, I'll just make the substitutions. I will get the vector field represented as a function of time. What wind vector am I feeling at each moment in time as I walk along the curve? And those are the two things you need to take the dot product of to get your integrand. So I changed the interval of integration, the set of integration. I changed the integrand. Oh, and then there's the differential. You know how you have to change that. You need to multiply by the lengths in the t real number line. And you have to multiply by that fudge factor, the stretching factor that talks about what's the difference between the interval in the t-axis versus the length of the arc in the xy plane. Or since I'm using the word time, you could say the little bit of length, you get length by multiplying your speed times the time elapsed. And there you go. Now you have an integral that's expressed in terms of t alone. And that's what you have to integrate. Integrate this function of t with respect to t on that range of t's. And I got to admit, it looks terrible. But good things are in store, because part of what makes this terrible looking is that you have the magnitude of these derivative vectors floating around. And you know, that's going to be some square roots of squares, and it's just really annoying in general. But this is the speed of your travel along the curve, and your speed shows up twice. We needed it in the denominator of the velocity here because we needed a unit tangent vector. And then we needed it over here as the fudge factor that stretched increments of time to become increments of length. So there's two appearances of the speed, but one's in the numerator and one's in the denominator, which means they cancel. So you have here a little gift from nature that the formula for calculating this line integral does not involve the speed at all. You simply take the dot product of the vector field that you experience at time t. You dot that with your velocity vector at time t. Since the speed isn't involved, there's no square roots of sums of squares now. Arguably, these line integrals are actually easier to compute than the path integrals. Doesn't look like it from this formula, but it starts to feel that way in this one. So I'll show you how to compute that in a second. Let me just show you the different notation that you might experience because of this. So, I mean, how are we going to work all this out? I'll have to take that vector field, which expresses its different components as functions of like x, y, and z, and then I'll replace the x's and y's and z's by those functions of t. So, you know, if they actually write out the vector field for you as, you know, so many x, y's, and z's in the first component, comma, a second component, comma, a third component, then this recipe asks you to replace all the x's and y's and z's by phi of t. You'll have to evaluate each one of these three functions separately. And then you need to take the dot product with your velocity vector, which is the derivative of the first component, comma, the derivative of the second component, comma, the derivative of the third component. And I've just written out the dot product for you. It's the product of two first components, second, third, you add them up. So this is literally what you're going to be integrating. It's a lot of symbols. In practice, people try to make all the t's go away, and they say, look, I just want you to take the first component of the vector field and the second and the third and multiply them by the first and second, third components of your velocity vector, your velocity in the x direction and the y direction and the z direction. And once you've simplified the notation like this, then you start to say, hey, why don't I pretend that these derivatives are just fractions, and then all the dt's in the denominator will cancel that dt. So purely for notational convenience, I can write my integrand out this way. So this is the way you often see a line integral written. You'll see a function of x, y, and z times dx, plus a function of x, y, and z times dy, and another one, in 3 dimensions anyway, there would be a third one times dz. Exactly what it means is what all these other ones have meant, okay? So this is just a little bit of notation that looks a little more elegant, perhaps, than all this kind of crap. I mean, sophisticated mathematical material. You could go back to the dot product notation. You will see people write it this way sometimes. They just gather together the f's and they gather together the differentials. And the main reason for doing that is you say, well duh, that if you just take the vector that has those 3 components, that is exactly what the vector field f was in the first place. And if this means a vector of a small displacement in the x direction and a small displacement in the y and z directions, well, it's just a small displacement vector. So we just write it as a ds. I don't know why s. I guess because you can't call it dd, d for displacement. There's too many d's. But it's a dot product. And so this is a notation that you will see. I might use this notation because I'm trying to still keep length in mind. So these are all different notations for the same thing. Don't be freaked out by the changes in notation. Some of them are a little more elegant than others. Some of them are a little more directly computable than others. But they all mean the same thing. So get in the habit of recognizing them and pick one notation that you like and learn how to change the other ones into that. And as I said at the beginning of the hour, you will recognize that you need to do one of these kinds of integrals because there will probably be a big black dot or some arrows to indicate vectors, or boldface to indicate vectors. And of course, there was probably a reference to a vector field at the very beginning anyway. Now, let me show you how we would actually compute these things in practice. I did one, I said I would be using things with the velocity vectors, since in general we don't have pretty geometry to help us get those unit tangent vectors. But here's how I would do it with the parameterization in mind. Let's go back to exactly the same line integral that we had before. So I already did the computation for this one, or at least I set it up. So it's a line integral now, and you notice that I'm trying to use a notation that is of this type. So it's stuff times dx plus stuff times dy. To actually do the computation, you need to parameterize the curve. And if you're on a unit circle, a circle of radius 2, this would be a parameterization that you could use. This range of t's would get you exactly halfway around the circle. And notice that I'm choosing a parameterization which is consistent with the little arrow that was indicated. When you start at t equals 0, you're here, and by the time you get to t equals pi, you're there. So now you have your parameterization, and the recipe that I told you to use up here says take the components of x and y and stick them into your vector field and dot that with your velocity vector. Well, okay, so here's my x and here's my y, and if I stick that in for x and that in for y right here, this is what I get. And same way with this other component, this is what I'm going to get. And the other thing you're going to take the dot product with will be your velocity vector. That's the derivatives of these two things now showing up in these two spots. And if you just, add all the terms together, what you get is a function of t. And you need to integrate it with respect to t between those two values of t. That's a Calc 1 problem. I actually worked it out and I gave you the number here. Okay? So this is how you tend to evaluate line integrals in practice. You begin with your parameterization. You simply make some substitutions and you take the dot product with the velocity vector. That's dx over dt and dy over dt times dt. And then it's a Calc 1 kind of integral. That's it. So for line integrals, there are the 3 different areas of what I want you to be aware of. You first have to understand what they mean so that they become path integrals once you realize that they are somehow being used to look at the contribution of a vector field in the direction of travel along a curve. You get used to that. Get used to those different forms of notation, and then learn how to do the computations, just like I did for you on this page. The only other thing to say about line integrals is this theorem. It's called the fundamental theorem of line integrals, and I wrote it out, and now I've lost it. Maybe I'll have to say it again. Oh, here it is. So here's the one theorem that I will leave you with, and this is one of the ones you would have needed this in that one exercise in the homework. Some vector fields are gradient vector fields of a scalar valued function. In that case, if somebody asks you to please compute this line integral along a certain path, it turns out you could do exactly the same thing that you did in Calc 1. You find the function that you were differentiating to get this vector field, and you simply evaluate it at the two endpoints and subtract. Which means, in particular, you don't need a parameterization of this curve. In fact, you don't even need to know what the curve is. You'll get the same answer irrespective of which curve you use to get from P to Q. Now, that's a very fortunate situation, but it only applies in the special case with your vector field happens to be the gradient vector of a scalar valued function. And we discussed this back in chapter 4. These situations are when you have what's called a conservative vector field. And if you have a conservative vector field, then all of the line integrals can be done very simply by you're in effect anti-differentiating this vector field. You're finding out what the function g is, whose gradient is the vector field that was given. There are other theorems about line integrals, but I won't hold you to them for the test. All right, you guys got pretty darn quiet today. Is there anything that you want to ask me about line integrals? Those are the 4 topics that you might want to ask me about.
Do you think you could go over a little bit more about how we know that the vector field is specifically a gradient vector that is scalar valued like you mentioned before?
Yep, that's a good question. How do you recognize a conservative vector field when you've got one? Because most of them aren't. And I can make that pretty clear to you just by looking at this one vector field that I gave you as an example. You'll see that this one is actually not a conservative vector field. And you know how I know? If it was, you would be saying that if you told me that this was, is it equal to the gradient of g, you would compute a gradient by taking the partial of g with respect to x and the partial of g with respect to y, right? But if that's true, then if I look at the partial derivative of this guy with respect to y, well, that should be giving me the partial with respect to y of the partial with respect to x of this function g. And in the same way, if I look at the partial derivative of the second component, but with respect to x, well, that would be a second partial derivative of g with respect to x and y in this order. Now, you know, I told you that earlier in the semester that for the functions that we deal with, all nice functions, these two expressions should be equal. And they won't be in this case. You see, this partial derivative is a 2 and this one is a 3. So the fact that these two partial derivatives are not equal is your clue that this is not a conservative vector field. And that is the general test. You need to look at whether the partial derivative of the first function with respect to the second variable is the same as the partial of the second function with respect to the first variable. That's the test for when your vector field is a conservative vector field. And if you're wondering about the three-dimensional case, the three-dimensional case would be very similar. It would be a bunch of statements about mixing the partial derivatives to get second-order partial derivatives that are supposed to be equal. But I can actually summarize all of that in the three-dimensional setting instead of writing down several equations like this stuff. Instead, the rule is that a vector field is a conservative vector field. That will happen if and only if the curl of your vector field is the zero vector field. I say if and only if there's some little technical requirements that I'm going to skip over in this course. They're actually very interesting, but for us, we'll just take this as an if and only if. So there's your test, even for vector fields in R3. I mean, when you write down what the curl is, it's just asking you to compute a bunch of these partials and see whether they match, but it's a succinct way of describing when a vector field really is a conservative vector field. All right, listen, I've hit the end of the hour. I've only gone over 1 minute today. This probably got to be a record for me. You have a test coming up it's on Friday, but what that's going to mean is we won't have class on Friday. Friday is when you're going to turn in your exam. But I'm going to make it available to you tomorrow, at midday tomorrow sometime. And it will have a quest component and a free response component. So just like the first midterm that you have, only this time the quest component, you will literally do it on quest. And the free response, you're going to have to scan your answers, unless you just want to type your answers, you'll have to write them out by hand and then scan them. And you can, I'll set up a way for you to do that on Canvas. You can email it to me if you can't make the Canvas thing work. Don't worry about that. But I'm going to give you plenty of time to work on the free response questions, and I'll give you 2 hours, which should also be plenty of time to do the quest problems. But just give yourself, set aside some time for you to work on these problems sometime between midday tomorrow and midday on Friday. Okay? Now, I've already been asked, I'm going to send you guys a nice sort of a summary letter, an email, that'll tell you all the little rules of what you're going to need to do for the test, just because I know we all have to face this technology stuff. But I'll outline in the email what you need to do, and I'll even put in there a summary of what the topics are, okay? So that's your exam, that'll be your exam, and it'll be due on Friday at the time of our class meeting. And I'll give you all the details in the email, okay? So take the rest of the day today, we'll finish those homeworks, make sure you understand all this material, ask each other for help on Piazza. I'll try to swing by and give people a hand. I still do have office hours today. And then I'll send you an email with more of the details about the test, okay? Alrighty, guys, good luck. And I'll expect an email from me. That'll be the next thing that we do.